Okay, good morning, everyone. So I'm a PhD student in Université Paris-Saclay. Today I'll talk about measurement catastrophes in quantum gem states. But first of all, let me thank the organizers and Filippo in particular for organizing this nice workshop. And as a former undergrad student in Florence, it's particularly nice to be back to GGI once again. So my talk is organized in 3 parts. In the first part, I will introduce the framework we work with. In the second part, I will specialize to a particular integrable model. And in the last part, I will give some results about that model. So let's get started. So we consider quantum spin chains, and we are interested in their behavior out of equilibrium. We will assume our models to be completely isolated from the environment, which means that they undergo a unitary dynamics. We can evolve the state with a unitary operator. We will also assume the Hamiltonian of the system to be time independent. So now let me point out that although there are 2 important assumptions here, that is the one-dimensionality of the system and the full isolation from the environment, those models are still relevant experimentally. And indeed, since almost a couple of decades, some experiments exist, like in cold atom physics, that can reproduce, that can build up setups that effectively behave like isolated one-dimensional models. So with that in mind, we want to consider the effect of local perturbations in quantum spin chains. I will introduce local perturbations with a classical analogy here. So assume to have a very large lake, and then at time 0 to throw a rock into the lake. So what happens is that some ripples form around the point in which the rock hit the surface. So initially the ripples here are very visible, but then if we wait some time, the dynamics of the system spread them all over the lake's surface. And if we wait like an hour, we cannot even be sure that the perturbation ever took place. So this is a case in which local perturbations, the effect of local perturbations is cancelled by dynamics. We want to consider the analogous effect in quantum spin chains. So in quantum spin chains, instead of having a lake, we will start with an initial state, an initial quantum state. We will take any typical physical state. So it can be like an eigenstate of a local Hamiltonian, or any statistical ensemble, like a Gibbs ensemble, generalized Gibbs ensemble. And to require this physicality of the state, we will require the clustering of correlation, expressed by this property, where here this expectation value is the connected correlation function. Then at time 0, we need to perturb our state, to throw our rock into our state. And in this case, this perturbation is represented by the application of some operator, any operator, to just few spin sites. Then what we do is we study what happens if we let the system evolve. So it turns out that the typical situation, the effects of this local perturbation are cancelled by dynamics. So if we wait long enough, we cannot distinguish the unperturbed case from the perturbed case. So let me give an example of the typical situation. Here I will just keep the level of discussion to a qualitative level. Let's consider the transverse field Ising chain with this Hamiltonian. This is a non-interacting model, so a lot is known about that. And so it presents a spontaneous symmetry breaking. There's a degenerate ground state. And we will take as our initial state one of the symmetry broken ground states. So let's take a ground state. So clearly, since this is the ground state, it does not evolve in time. But then at time 0, we apply our local perturbation. In this case, we take as a local perturbation a spin flip along the z-axis, which is represented by the Pauli X matrix applied to the origin. So this flips the spin along the z direction in the origin. And here I reported the simulation for the profile of magnetization along z direction normalized with the value that magnetization had before the local perturbation. So time zero, in any point, the magnetization is, normalized magnetization is 1, except at the origin where the spin flipped the sign of the magnetization. If we now wait some time, there's the analog of ripples that appears around the point in which I perform my perturbation. Then as time goes by, this effect is less and less visible. So it spreads all over the quantum chain. Eventually, locally, one cannot be sure that the perturbation ever took place. So this is an example of how the effects of local perturbations are cancelled by dynamics. But clearly, if I'm talking about that, it's because there are exceptions to this effect, and that's what I'm interested in. So let's give an example also of an exception. Let's still consider the Ising chain, and let's start still with the ground state. But this time, instead of flipping the spin along Z direction, we flip a spin along X direction. Now, this is a special perturbation because it's linked to the broken symmetry of the system. Essentially, it's linking the two symmetry broken ground states. So if we now look at the profile of magnetization along the X direction, which by the way is the order parameter, at time zero, it looks exactly the same as in the previous slide. It's normalized, it's 1 everywhere except at the origin where the spin flipped the sign. But now, if we wait some time, instead of having some ripples that form and then spread around, we have a non-trivial profile that emerges, and it never fades away with time. So there are, and actually, there's a diverging number of spins that is involved in this effect. So we say that in this case, effects of a local perturbation, of this local perturbation, have everlasting macroscopic effects. So everlasting because they are there for any time, and macroscopic because they involve a number of spins that diverges with time. Yeah. It's highly non-local. Yeah, definitely. That's an important characteristic that a perturbation must have in order for it to have a. No, it shouldn't. It doesn't depend on the basis. No. It's a string operator. Not this one. The perturbation is local also in fermions. I use the basis that diagonalizes the Hamiltonian. Of course, the choice of the basis depends on the Hamiltonian. And in the basis that diagonalizes this Hamiltonian in fermions, this perturbation is local. It consists of 2 Majorana fermions, for example. But then the observable we are looking at is highly non-local. It's a string of Majorana fermions, for example, or of sigma Z spin chain. And that's an important property that the observable should have in order to see an effect of this kind, because if it's local both in spins and in fermions, then we are sure that it fades away with time, the effect. That's a good remark. Okay, so this is the kind of situation I'm interested in. Let me stress out again that this is not at all the typical effect. Indeed, to the best of our knowledge, there are only 3 classes of models in which an effect may have an everlasting macroscopic effect. And so the first class was studied first numerically by this group and then analytically by Victor Eisler and his group. And it consists of models exhibiting spontaneous symmetry breaking with a local perturbation that links the degenerate ground states. But I will not talk about that anymore for today. And the second class is what I'll focus on for the rest of the talk, and consists in models exhibiting quantum jamming, and I will introduce them soon. And it was studied by my collaborators and me. And finally, there's a third class in which such a phenomenon can be seen, and it's linked to systems presenting semi-local charges, and it's linked to what Lennart would have talked about yesterday, but sadly he couldn't. So, but I will not talk about those for today. So for the rest of the talk, I will just focus on this second class and give an explicit example from this class. All right, so let's specialize to a specific model. The model I'll consider for the rest of the talk is called the dual-folded XXZ chain. It was originally introduced to describe the large anisotropy limit of the famous XXZ chain. It is by itself an interacting integrable model, which corresponds to a special point of the Bariev model for those who know it. But however, for the rest of for the sake of my talk, I will not need the connection to the XXZ chain, and I will not need to know anything about the Bariev chain. In fact, I will not even use explicitly any integrable technique. The only thing we need to know about this Hamiltonian is the dynamical rule that can be read off from it. Like, so what this Hamiltonian does is it describes a constrained hopping model in a spin chain. So if we specialize for the moment to the Z basis, in which the quantum states are described only by spins up and down, if now there's a constrained hopping in this chain from this Hamiltonian, so if we have a spin up and a spin down that are nearest neighbors, they can exchange if the spin in between points downwards. So essentially in this configuration, they cannot exchange if the spin in between is up, and they cannot exchange if they are the same. So if both spins are up or both spins are down, they do not exchange. So this is the dynamical rule that we will need. Now, a convenient picture to work with when describing the dual-folded XXZ chain is that of a quasi-particle picture. So let me introduce this mapping. So we take our chain and we divide the spins in couples, and then to each couple we assign a macrosite. Then at this point, we look at the spins up. So if we take a macrosite, if the first spin of the macrosite points up, like here, we say that the macrosite is occupied by an orange particle. If the second spin of the macrosite points up, we say that the macrosite is occupied by a blue particle. Now, clearly, the macrosite can also be empty if both spins are down, and it can be occupied by both species of particles if both spins are up. So this allows us to map any state of the Z basis into a state of quasi-particles. And now to complete the mapping, we also need to translate the dynamical rule for spins into a dynamical rule for quasi-particles. Now it turns out that the dynamics for quasi-particles it's a nearest neighbor jumping with a hardcore constraint. So essentially, particles can jump to nearest neighboring sides if they don't find any other particle in between. So if the site is empty, of course, they can always jump, but they can also jump if the neighboring site is, like, for example, this orange particle can jump to the right to this site occupied by a blue particle because of their triangular shape. So here the shape is important. Now, already from here, we can draw two important conclusions. So first of all, the sequence of particles is preserved. And that's because of the hardcore constraint. They cannot exchange. So the sequence of colors stays the same. For example, this blue particle cannot jump to the left of this orange particle because it clashes with it. And also we can remark that if our macrosites are so packed with particles that they can essentially find the particle immediately when trying to move around, then no dynamics can happen. And we call those states that are too full of particles to move, we call them jump states. So this will be important. All right, now I have all the ingredients. I will just need to introduce our local perturbation to link to the first section of the talk. So our initial state will be a jump state, and no surprise here. And then at time 0, what we do is we flip a spin, and in terms of in such a way that the resulting state is not jumped anymore. So in terms of quasi-particles, it amounts to removing one particle. So initially the state does not evolve because it's jumped, but now removing one particle, it enables dynamics around the perturbation. Now, importantly, we can read this local perturbation as a local measurement, projective measurement, actually 2 of them. So if we start with this spin up, for example, we can first measure the magnetization along x direction, and right afterwards the magnetization along the z direction. And one possible outcome of the projective measurement is this one, in which the spin is flipped. Now, I said I will not have time to talk about that, but looking at this local perturbation as a local measurement allowed us to compare our result with some important protocols in quantum information, like specifically the wing flap protocol. Yes. No, okay, I have not specified the boundary. In fact, in all my results, I will take the length of the chain to go to infinity. Of course, yeah, okay, yeah, no, you're right. You mean in defining the macrosites? Yeah, no, you're completely right. And actually, if this chain is odd, we cannot. This definition does not even make sense if we have boundary conditions or open boundary, because in open boundary one is left alone with the periodic. It also does not make sense. So for convenience, we could say, for the sake of the talk, we specialize to even length, to an even length of the chain. And then the boundary, you can choose the boundary you like, because in the end I will take the size of the chain to infinity. And since the state does not evolve, there will still be this ambiguity in the choice of macrosites, but one can show that it doesn't matter. It's just a convention, in fact. And actually, we could even extend the discussion to odd lengths of the chain, and in that case, also there's a way to overcome this problem. But yeah, eventually I'll take the chain to go to infinity, and since it does not evolve, and since we have the Lieb-Robinson bound on the propagation of information from the boundary, we don't care about the information at the boundary in this case. Okay, so from the rest of the talk, I will refer to this local perturbation as a local measurement. So once we have done that, we let the system evolve, and we study what happens. What we will see is that this local measurement has an everlasting macroscopic effect of the kind that we introduced in the first section. And so we will refer to it as a measurement catastrophe, because it's an effect, it's a peculiar effect that we get just from a local measurement. The whole chain eventually reconfigures due to this local, only because we have looked at one side of it. Okay, so let me go to describe the main idea that allowed us to solve the problem. So here I reported an example of a jump state in which I took away a particle, and the first 2 applications of the Hamiltonian. There are 2 important observations here. The first one we've already done is that the sequence of particles is conserved. So initially it was orange, blue, orange, orange, blue, blue. So, and it stays the same for any state that I can obtain by applying the Hamiltonian. Also, for any state that I obtain by applying the Hamiltonian, any state is essentially a jump state, except for one impurity. It's jumped everywhere except in one point. So to specify any of those states that I can obtain, it's sufficient to specify the background, so the configuration of particles, which is determined from the start, from the initial state, and the position of the impurity. So now this simplifies a lot our problem, since we can describe everything in terms of just one hopping impurity that for each application of the Hamiltonian jumps over the nearest neighboring quasi-particle. So this simplifies a lot, because now we end up with a single particle problem jumping to nearest neighbors, which is a non-interacting model. But let me stress out that this does not mean that the initial problem is non-interacting, because the mapping here is non-local. So the interaction is kind of hidden in this non-locality of the mapping. That the mapping is non-local, it can be already understood from the fact that this effective lattice length equals the number of quasi-particles. So it depends on the content of quasi-particles of the whole initial state. Okay. So now, using this one particle physics, which is the XX chain, and paying extra care for this non-local mapping, we can compute the asymptotic value of essentially any local observable. I reported here the example of magnetization along Z direction in the scaling limit, in which I take the time to go to infinity and I rescale the position accordingly, so the position, the site position. So remarkably, to get the asymptotic value of magnetization, we just need a few initial elements. So just the position of the impurity at time 0 with respect to the position I'm looking at, and only the configuration of 3 adjacent spins around the position I'm looking at. There's also an important parameter here, x of L, that in which we can see the non-locality of the mapping, which essentially counts the particle content between the origin, where I've done my perturbation, and the site I'm looking at. So this is a non-local parameter that counts the particles in a macroscopic part of my chain. Let me give an example of the application of this asymptotic result. We can start with a jump state of this form. So with a 3 periodicity, spins up, up, down, repeated in the whole chain. In this case, this parameter for a very large L is approximately 2/3. So we can plug this in and compute the magnetization profiles in the rescaled ray coordinates, in which we take L over T to describe the scaling limit. So without the perturbation, the profile of magnetization would have been just in +1 and -1, because the initial state would not have evolved. So in this case, instead, we get non-trivial profiles that involve a number of spins that grows linearly with time. So this is a macroscopic region of spins with the size that scales with time. So this is indeed a local measurement that gives an everlasting macroscopic effect. So this is what we call a measurement catastrophe. Okay, that's the main result that I wanted to show. Let me just flash another interesting property of this protocol. So if we now look at currents associated to these to observables, like in this case, the current associated to magnetization, we can show that the expectation value of any current goes to 0 in time. So we have those non-trivial ballistic profiles that emerge in time with a vanishing current. So what this tells us is that this effect is a consequence of a local reorganization of spins, but there is no actual spin transport in this problem. It's really a peculiarity of these jump states. Okay, but this is just a remark I wanted to make. I think I'm more or less out of time, so let me summarize the things I've been telling you. So we gave, I presented you a way to get the explicit solution to a truly interacting model, but restricting us to a specific jump sector, which simplifies things. I've shown that there are some local measurements that produces catastrophes, like effects that do not fade away with time and involve a macroscopic number of spins. And I've shown that, told you that this happens with no genuine spin transport involved. So now a few directions that we could go towards are like, so we strongly suspect that this property of measurement catastrophe, we suspect it to be a shared property by all models exhibiting quantum jamming. We still have to prove that, or at least show that. Or I've told you that there exist 3 classes exhibiting some local perturbations with everlasting macroscopic effects. And so I didn't tell you, but I'll tell you it now. Like generalized hydrodynamics, which is the most famous and useful technique to deal with inhomogeneous dynamics for integrable models, it doesn't work in this case because any hydrodynamical approach is not sensible to just one spin, just a configuration of a single spin. So the usual hydrodynamical techniques do not work in my case. So it would be nice to like either extend them or come up with a theory to describe all the classes I've presented with this effect all together under the same framework. And finally, and this is a project I'm working on right now, I haven't talked about that, but like there are interesting entanglement features in these protocols. So hopefully in the next talk, I will talk about that. So this is all. Thanks for your attention.
Any questions? Yep.
So are there examples of jam states and measurement catastrophe in chaotic spin chains?
Okay, that's definitely interesting. Chaotic spin chains, you mean like breaking integrability if the effect persists? In fact, it does. We have checked that. Not analytically, though, because we lack integrability and this mapping to quasi-particles. But we have tried with the same Hamiltonian, like that we have here, to add an integrability breaking term that we constructed essentially putting together 2 of these terms with different sides. It breaks integrability, and we witnessed the same effect, but now instead of being on a ballistic scale, it's on a diffusive scale. So the profiles, we will get those asymptotic profiles by rescaling the position with the square root of time instead of with time. But yeah, the effect persists at least, but okay, it's still related to this model. We have not checked it in other models because usually it does not happen. It's a peculiar effect of something that gives this everlasting macroscopic effect. So we have to engineer a bit the system. But yeah, thanks for the question.
Just as you just answered the previous question, I mean, if there's only one impurity, why does it matter whether this model is in?
Okay, but it's not just a one particle problem. So let's see, the elementary excitations here of the integrable models are these quasi-particles, and our jump state has a lot of them. In fact, it's fully packed with elementary excitations. But then yeah, the impurity, okay, the impurity is just one particle problem, but it's sensible to the full content of particles inside the initial state. because of this non-local mapping. So it's true. It's one in this mapping here. It's a one particle problem, but it's still sensible on the whole particle content of the initial state. Yeah, that's it's essentially it is. Yes, what is dressed is like this effective position, if you wish. This X of L is kind of an effective position that depends on how many particles are between the perturbation and the position I'm looking at. So this is an effective position, if you wish, that is dressed by the whole particle content of the state. Two holes, okay, two impurities, yeah, okay. Okay, so now, of course, if they are far apart, the effect is the same because still of Lieb-Robinson bound. But even if we put them close, we still get some, at least if they are finite in number, we still get some non-trivial profiles. And now getting them analytically is more complicated because it's not a one particle problem anymore. And okay, and also it's not even in general, it's not even a two particle problems because the particles would interact in I mean, not a free particle. It would be a two particle problem, but not free. For the impurities here, okay, I'm not sure. Okay, probably, I don't know, I have not looked at that. Maybe, okay, maybe my collaborators have. We should ask them, but no, okay, I don't know about that.
Yeah, I just want to comment that in principle you can consider like normal mobile impurity propagating in 1D system, and there will be similar phenomena.
So it would lead. Yeah. Okay. You say the non-locality in the fermion space, like if we map the fermions. Okay, that's necessary but not sufficient. You know, of course, non-locality in fermions is important. As I was telling Johan at the beginning, if it's local both in spins and fermions, we don't see this effect. So non-locality in fermions is important here. But it's not sufficient at all, and in general it does not happen. I mean, generally you see some perturbation, that spreads all over the chain, and then the effect disappears. But and in momentum space, okay, I see. Okay, yeah, but the problem would be then to find some observable indeed to present. Okay, well, we can discuss about that.
Oh, maybe this is a stupid question, but why is it that you can coarse grain these two beings into blocks if they are Hamiltonian?
I'm ignoring, I didn't get, it's a bit low, the volume, so I'm ignoring I didn't get what I'm ignoring. So I have this translation in invariant Hamiltonian. Yes. Yeah. Okay, yeah, we trade these three interactions with two species of particles. So like, yeah, maybe it's more clear from here. Like to get this rule of jumping of the orange particle, for example, we would look at these three spins. So these three spins is exactly this dynamical rule. So what happens in these three spins is that this spin up can exchange with this spin down, because the spin in between is down. So it jumps here, and effectively in the particle language, it means that the orange particle jumps to the right. Yeah. Okay, let's write some. Like if I have some, can you see from the? Okay. Yeah, okay, yeah, this is the minimal pattern. Like with the spin, even with the spins, if I have more, it can. There are multiple jumps that happen with the one application of the Hamiltonian. Like. You mean the translational invariant? Like this would be some kind of non-translational invariant term, or? Okay, no, here I'm considering in the spins I'm considering the Z basis. Then if I have a general state, I will have a superposition of all those states. So this is in this case. Okay, here I'm really considering the Z basis. Then I can decompose any state in that basis, and having a mapping from the basis of the Z basis to a basis to particles, that allows me to map any state into a particle state. Then okay, the rule, like if I put two spins together, like this state would not evolve. I always need two spins down in the state to let it evolve, to make it evolve because of the spin rule dynamics. So I need always two spins down for the state to evolve. And indeed, jump states in the spin language, those are all the states that do not have two spins down, two consecutively spins down. So if I write any state without two spins down, like that, this is a jump state because there are no two spins down. And in terms of particle, you can translate it into, in this case, it would be like that. Here, there are both particles. Then there's another particle like that. Okay, let's take just to vary a bit. I take for convenience the chain to be even, but because I will take just for convenience, because I'll take an infinite chain. Yes. Yes. And also here, in fact. Yeah. If you have to. Yeah, there are two ways. Yes, I could shift everything by one side. It was still a jam state. The particles would be, the particle configuration would be different. We can even do that. Like let's shift this by one, and then it's down, up, 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 down, up, up, down. So this is the same state. I've shifted everything by one. So the particle content changes. Now we have two particles here. This is this particle, two here, and one like that. So the particle content has changed, but the state is still jammed. And we can show it's really a matter of convenience, a matter of convention, or which one to assume. It's still one bijection that we define to a problem that simplifies our problem. And yeah, the result, the final result does not change in the end.
Okay. I think if there are no more questions, we thank the speaker again.